Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about the force between two long straight current carrying wires and how it helps to give us an operational definition for the ampere. Thus we can make use of Ampere's law to define the unit ampere or amp, which is named after Ampere, who sort of discovered Ampere's law. So I guess the main thing that we would need to recall, the main video you need to have watched before this one, is the video on Ampere's law. So in some sense this is an application of Ampere's law. From an algebra-based physics perspective, Ampere's law just says that if I go around a complete closed path and add up around that closed path all of the B dot dl terms needed to make that closed path, that I should get this fundamental constant mu naught times the enclosed current, that is the current that's enclosed by this path. And of course mu naught is the fundamental constant permeability of free space, and so it has a value of 4 pi times 10 to the negative 7 Tesla meter per amp. So that is again a fundamental constant of the universe. The rest of these, you know the magnetic field, you know the current, you know the delta L. And we typically draw this situation for, let's say, a long wire that is carrying charge. So maybe I have a wire like this, and I happen to have, I said carrying charges, carrying current. Charges are moving in the wire, let's say. So there's somehow a current in the upward direction. And then our closed path might be this circle. And so each of the little segment of the circle could represent the delta L. That includes these open parts. And we would basically just need to use all the delta L's around this loop combined with all of the magnetic fields that are around the loop. And the magnetic fields in this case are also circular in nature. And so that then gives you this magnetic field strength in terms of this current that's inside the wire, and in terms of really how far from the wire you are, because delta L, when you add all this up, ends up being B times delta L summed is just a 2 pi times radius times the magnetic field strength. So if this has some radius r, then we end up being able to write something like 2 pi r b is equal to mu naught I. And from that we were able to solve for the magnetic field strength B from this current carrying wire. Now where the application of this comes in today is that we also happen to know what kind of force is applied to a long straight wire by a magnetic field. So further things to recall. Recall part 2, if you will, that the force on a current carrying conductor due to a magnetic field, we can call it FB if you'd like, is the current carried by that conductor times the cross product between the length vector and the magnetic field vector. F equals ILB. Okay, and so in this case the length vector is to be distinguished from the delta L vector that we used over here. This length vector points in the direction that the current is traveling in. So if I happen to have a current carrying wire, let's say again that it is like this, and I've placed it in an external magnetic field. So I have current in the wire here, and I place this wire in a magnetic field, let's make the magnetic field be, maybe uniform but external to this wire. So this is maybe my magnetic field direction, B. We could even call it B external up here to distinguish it from the field that's being produced by the wire. Well, the cross product in this case, my L vector, basically would point from here to here, basically from one end of this wire to the other end of this wire. And so L cross B would have a magnitude, or L cross B external would have a magnitude of L times B times sine of whatever angle is between the two of them. And so here's my L vector pointing this way, and my magnetic field vector is pointing this way, so this would be angle theta. So basically what this means is I have L cross with B, and that ends up being a force into the page. Alright, so these two facts can be combined by saying, what if we happen to have two long straight current carrying wires? So here I have a wire, and it's going to carry some current. Over here I have another wire, and it's also carrying some current. And the two currents may be in the same direction, or they may be in opposite directions. So I may have like I1 going this way in this wire, and I may have I2 going the opposite direction in the other wire. They could be in the same direction, etc. Now it should be evident, just in looking at this, that wire number 1, we can call this wire 1, and we could call this one wire 2. It should be evident that wire 1 is going to produce a magnetic field, and that right here at the location of wire 2, the magnetic field actually is into the page. And so if I were to draw a representation of this magnetic field at the location of wire 2, we could call this B1, and this is going to apply some force on I2. By the right-hand rule, that force, let's do it maybe in green here, will actually act in this direction. We could call this the force of wire 1 on wire 2. Alright, and now we can do the same thing with wire 2. We know that it produces a magnetic field on wire 1. Alright, B2 at the location of wire 1, B2 due to wire 2, is actually once again into the page, because the current is pointing downward here, and so by the right-hand rule you end up wrapping with a thumb down. Current's going to actually be into the, or the field is going to be into the page on this side. And it need not have the same magnitude as the field from produced by wire 1 at the location of wire 2. In fact, it would only have the same magnitude if these two currents are the same, which they could be, but they need not be. These could be powered by separate sources or something. Alright, so now let's do our cross product to find the direction of the force in this case again. So I have B2 into the board, or into the page, or into the screen, and I have that L1 is up in the direction of the wire number 1. And so if I put those two things together to get the direction of this force, and I use the right-hand rule, I'll find that the force in this case from wire 2 on wire 1, we could call this F21, is actually pointing to the left. F12 is to the right, F21 is to the left. Now for what it's worth, I'm not going to do this in this video, but if you were to change this so that this current I2 is also upward, or so both current point up, or if you change it so both current point down, then the two forces will actually be directed towards each other. So if the currents are in the opposite direction, you get sort of a repulsive force. If they're in the same direction, you get an attractive force. I'll let you think about which of these two forces is the larger, if they're equal. If we were to assume, let's say, a standard separation of R, but this current is maybe 2 times bigger than this current. Think about, like, what is the ratio of these two forces? Is it 2 to 1? Is it 1 to 2? Is it 1 to 1? Etc. I'm moving on though because, and this is in some sense an example, but it's like the ampere. So the unit named after Ampere. What is an operational definition for it? Well, if I wanted to get the force, I've got these equations here, and ultimately we ended up saying, instead of how much force, we said how much force per unit length, and that ended up being current times B field times basically sine of theta. So if I come down to this system and I again say, okay, what's the force, let's say, on wire 1 or on wire 2 due to wire 1 per unit length, again, of wire 2. That should be the current in wire 2 times the magnetic field from wire 1 times the sine of theta. But we know that theta is 90 degrees because B and IL are perpendicular vectors. There may be like a sign, a plus or minus sign if we're keeping track of directions, but the magnitude of sine theta is just 1 in this case. Alright, so that's the force per unit length. We also have Ampere's law, so we know how much magnetic field B1 is present at wire 2. Basically, we have B1 at the position of wire 2 is equal to mu naught times the current I1 flowing through wire number 1 divided by 2 times pi times R, where we're defining R to be the distance between the two wires. We can therefore combine these two equations to get the force per unit length acting upon wire number 2 due to wire number 1. Basically substitute this expression for the magnetic field B1, and what you get is mu naught I1 I2 divided by 2 pi times R. Now from here we can actually do a sort of example, but it's really more of a how is it that this helps us define the unit of the ampere. Alright, suppose that each wire is carrying a current of exactly 1 amp, and suppose further that they are exactly 1 meter apart. We want to determine how much force per unit length is acting on one of the two wires. They should have the same force per unit length magnitude-wise. So force per unit length, if we were to do the wire 2, for example, F12, per unit length is over L2, should look like mu naught times I1 times I2 divided by 2 pi R. Now coming up here, each wire has exactly 1 amp, so I1 equals I2 equals 1 amp. They are also 1 meter apart, so R is also equal to 1 meter. So if we were to plug numbers into this equation, we have 4 times pi times 10 to the negative 7 Tesla meters per amp times these two currents. So we have 1 amp times 1 amp divided by 2 times pi times 1 meter. And so what we end up with is 2 times 10 to the negative 7 Tesla Tesla amps. Or if you'd prefer the unit in terms of force per unit length, this is 2 times 10 to the negative 7 newtons per meter. These are equivalent units. In any case, we now have an operational definition for an amp. 1 amp of current is the amount of current needed to produce 2 times 10 to the negative 7 newtons of force per meter length of wire for 2 very long, very straight wires which are 1 meter apart. This is an operational definition for the basic unit of current that doesn't actually need to refer to coulombs, to the charge of an electron, the charge of a proton, the fundamental charge, any of that, but instead can refer to 2 macroscopic items, two wires basically, which are carrying some amount of current. Now this is still a very small, you could say microscopic, it's actually even sub-microscopic in some sense, force. It's like 0.2 micronewtons per meter of force. But it is a measurable force with a sufficiently sensitive force scale. So this gives us a measurable, or a means of measuring something that we can then use to define what is this unit of current, the ampere. So that's all for today's video. Thanks for watching and hope you learned something. See you in the next video.